My mom's calling.
Did you take the meat out of the freezer?
The meat?
Yeah, the meat.
Out of the freezer?
Out of the freezer.
Oh yeah, I did that hours ago. No worries. It's fine. Okay, see you soon. Bye.
Did your mom ever tell you to take the meat out of the freezer and into the sink and you forgot? And now you have 30 minutes to defrost the whole chicken and have no idea if it will defrost in time. We'll see if simple heat transfer concepts can help us find a faster way to thaw it via liquid water or gas, air.
Our experiment explores heat transfer across an interface. But you may be wondering, what is heat transfer and what's an interface? Heat transfer is a discipline of thermal engineering that concerns the generation, use, conversion, and exchange of thermal energy between physical systems. This can be modeled as a cylinder and a glass of water, or as meat defrosting on a countertop. An interface is something we will also see in this video, and it is the point where two systems interact. For our purposes, we will show a solid gas and solid liquid interface. The primary equation we will be using to demonstrate heat transfer principles is Newton's law of cooling, which is a very common equation found in chemical engineering, and it only requires a few variables. Q being the rate of heat transfer, A being surface area, H being convective heat transfer coefficient, and delta T being the change in temperature. Certain things do influence how large or small Q is, one being material. What type of material is the object, and what type of material is the object in? This influences constants like density, heat capacity, and viscosity, which then influence the heat transfer. Geometry is also very important as it determines the type of formula used to calculate heat transfer. In our video, we will be using formulas related to horizontal cylinders. This is because the surface area to volume ratio and distribution changes with the geometry of the object. Lastly, convection type is very important. Free convection is fluid motion due to difference in density or temperature, and that is the type of convection we will be using in our experiment. Think of naturally flowing air. Forced convection, on the other hand, is when there is fluid velocity, like wind or a fan.
Here's an easy experiment you can do at home to demonstrate how free convection through liquid has higher rates of heat transfer than through a gas. For our list of supplies, we need 2 small cylinders, a large bowl of room temperature water, a thermometer, a freezer, string, and some tape. First, you put both rods in the freezer for 10 minutes so that they are both the same temperature. Then, take both rods out of the freezer and measure the temperature. Then, after that, put one rod in the bowl of water and the other rod in the knotted string suspended in the air. After 30 seconds, take the temperature of both rods. You'll see that the rod of the water heated up way faster than the rod in just open air.
In order to calculate the rate of heat transfer, we first begin by calculating the Nusselt number. The Nusselt number for a horizontal cylinder is given by this empirical correlation. In order to find it, we first need to find two other variables to plug into the equation, the Rayleigh number and the Prandtl number. The Rayleigh number is found by multiplying the Grashof number by the Prandtl number, and the Grashof number is calculated using these system constants shown here. The Prandtl number is also found by various system constants, and those constants are all evaluated at the film temperature, which is the average of the air temperature and the surface temperature of our cylinder. Once we get the Nusselt number, we can plug it into this equation here in order to get H, our convective heat transfer coefficient. After we have H, we can plug that into our Newton's law of cooling and calculate Q, which is our rate of heat transfer. Here's our measured data for our cylinder system. First up, we have the dimensions of the cylinder. Next, we have the temperature data that we measured using the IR thermometer. Using the film temperature and the numbers from the previous slide, we were able to calculate the Grashof number, the Prandtl number, and the Rayleigh number for both the air and water cylinders.
Here, you can see we used data from the previous slide, including the Rayleigh number and the Prandtl's number in green and red respectively, to calculate the Nusselt number for the system where the rod is in the air. We then use this Nusselt number to calculate our HD value, which we can then use to calculate Q, which is the total heat transfer over the actual rod itself. On this next slide, you can see we did the same calculations. However, here we used a different Prandtl number and a different Nusselt number to calculate our system because this is in the water. In this case, you'll notice that our HD value is different, and therefore our Q value is also different, which makes sense in this system as the water had a much larger change in temperature than the air did.
This tells us that, in general, when we want to cool or heat something in a short period of time, it's better to use a liquid than a gas. Almost every single factory and industry setting uses this principle. Some specific examples of that are heat exchangers, power stations, and HVAC systems. You might even use this on a smaller scale, like a gel compression pack being used to transfer heat to and from the body. So remember, folks, when you forget to take the meat out of the freezer, don't worry. Just put it in some hot water and your parents will never know you forgot.